Imagine a world where code is not written but painted, where algorithms are expressed not in text but in vibrant hues. This is the world of P-VPL, the Pantone Visual Programming Language. P-VPL is not your typical programming language. It discards the constraints of textual syntax, instead embracing the intuitive language of color. In P-VPL, each Pantone color becomes a fundamental building block of logic. A rich cobalt blue might signify a variable assignment, while a fiery crimson could represent a conditional loop. This marriage of color and code unlocks a new dimension of creative potential. It allows us to think about programming in a fundamentally different way. P-VPL is more than just a novel way to write code. It's a bridge between the worlds of art and logic. It's a testament to the idea that even the most complex algorithms can be expressed in a language that is both beautiful and powerful. At the heart of P-VPL lies a carefully crafted color lexeme mapping. This mapping forms the vocabulary of our visual language, connecting each Pantone color to a specific programming concept. Think of it as a dictionary where the words are colors and the definitions are the building blocks of code. Some colors represent fundamental programming structures. For instance, a deep forest green signifies the beginning of a function definition. A sunny yellow indicates the end of that function's scope. Control flow is dictated by a spectrum of blues and purples, with a cool indigo representing a conditional statement and a vibrant violet denoting a loop. But P-VPL goes beyond mere functionality. It incorporates a layer of emotional resonance by mapping certain colors to specific emotions. A calming teal represents the feeling of joy, while a fiery orange embodies anger. This emotional layer allows programmers to imbue their code with a depth of expression not found in traditional languages. In P-VPL, code is not written line by line, but rather it's constructed on a grid. This grid serves as our canvas, and the Pantone colors are our paints. Each cell on the grid can hold a single color, representing a single lexeme or instruction. The spatial arrangement of colors on the grid dictates the flow and structure of the program. Code is read from left to right, top to bottom, much like a page of text. However, the use of color introduces an element of two-dimensionality. Blocks of color can be nested within each other, representing nested loops or conditional statements. This visual syntax allows for a more intuitive understanding of program flow. The relationships between different parts of the code become immediately apparent, as if the logic of the program has been laid bare for all to see. Transforming a canvas of color into executable code requires a specialized compiler. The P-VPL compiler is a marvel of engineering, capable of understanding and interpreting the language of light. It consists of 4 main modules, each playing a crucial role in the translation process. The first module, the color reader, analyzes the input image and identifies the specific Pantone color present in each cell of the grid. This information is then passed on to the lexeme resolver, which uses the color lexeme mapping to determine the corresponding programming concept for each color. The execution engine takes the resolved lexemes and executes the program logic step by step, following the flow dictated by the spatial arrangement of colors. Finally, the symbolic mapper comes into play when encountering colors representing emotions. It translates these emotions into specific program behaviors or outputs, adding an extra layer of expressiveness. What sets P-VPL apart is not just its visual nature, but also its inherent multi-layered approach to meaning. Every program written in P-VPL operates on 3 distinct levels: the logical, the symbolic, and the recursive. On the logical level, P-VPL functions like any other programming language. Colors represent instructions, and their arrangement dictates the program's flow. The compiler translates these colors into machine-readable instructions, allowing the program to perform calculations, manipulate data, and interact with the world. The symbolic layer emerges from the mapping of colors to emotions. This allows P-VPL programs to not only execute tasks, but also to evoke feelings and convey artistic intent. A program that generates music, for example, might use specific color combinations to evoke feelings of joy, sadness, or anger in the listener. Finally, the recursive layer stems from P-VPL's visual nature. The ability to nest blocks of color within each other allows for the creation of fractal-like structures, mirroring the recursive patterns often found in nature and mathematics. This opens up exciting possibilities for exploring complex systems and generating intricate self-referential art. To facilitate the creation of P-VPL programs, a suite of specialized tools has emerged. Integrated development environments, or IDEs, for P-VPL often resemble digital art studios more than traditional code editors. Instead of typing lines of text, programmers use a palette of color tiles to construct their programs visually. These IDEs often include features like color pickers, drag-and-drop interfaces, and real-time visualization tools to make the programming process more intuitive and engaging. Some IDEs even incorporate AI assistants that can suggest color combinations based on the desired program behavior or emotional tone. On the compilation side, specialized camera compilers have been developed. These devices can capture an image of a P-VPL program created physically using colored tiles or paint. The compiler then analyzes the image, identifies the colors, and translates them into executable code. The applications of P-VPL extend far beyond traditional programming tasks. Its unique blend of logic, symbolism, and visual expression makes it a powerful tool for a wide range of fields. In the realm of creative coding, P-VPL has opened up new avenues for artistic expression. Artists are using P-VPL to create generative art, interactive installations, and even musical compositions. The ability to program with color allows for a more direct and intuitive connection between the artist's vision and the final artwork. Beyond the art world, P-VPL holds promise in the field of symbolic AI. Researchers are exploring its potential for developing AI systems that can understand and respond to human emotions. Imagine AI therapists that can interpret the emotional content of a patient's speech, or AI companions that can adapt their behavior based on the user's mood. P-VPL also has the potential to revolutionize education. By making programming more visual and engaging, it can help break down barriers to entry and empower a new generation of creators. Imagine children learning the fundamentals of coding not through lines of text, but through playful experimentation with color. P-VPL is more than just a programming language, it's a philosophical statement. It challenges our preconceived notions of what code is and what it can be. It forces us to confront the profound relationship between light, logic, and human emotion. In P-VPL, light is no longer just a source of illumination, it's the very fabric of thought. It's the medium through which we express complex ideas and build intricate systems. Color, with its inherent emotional resonance, becomes a bridge between the logical and the affective, allowing us to imbue our creations with a depth of feeling previously unimaginable. P-VPL invites us to reconsider the nature of creativity itself. It suggests that perhaps the most elegant and expressive forms of code are not written, but painted. They are not confined to the rigid structure of text, but flow freely across the canvas of our imagination, guided by the language of light and color.